Let us try to understand the meaning of surface integral and the technique to solve it. Earlier, we have defined a line integral by integral v bar dot dl bar, where this dl bar is infinitesimally small line element. On the similar basis, now we can define a surface integral as integral v bar. Of course, this was defined on a specific path. Similarly, this is to be defined on a specific surface S. So v bar dot dA bar. Now this dA bar is an infinitesimally small surface element, and in order to make it vector, we usually imply this technique. This dA bar is supposed to be dA times n cap, where this n cap is a unit vector perpendicular to the surface. Now suppose this is a particular surface element having area dA. Now this n cap can have one of these two directions, either vertically upwards or vertically downwards in this case. So conventionally, any one of these can be taken as positive direction, and the other obviously then becomes a negative direction. This is a complete matter of convention. As we have already defined a closed integral for the line integral part, where we start from some point A and end up on the same point A, so that the path becomes closed. Similarly, we can define a surface integral over a closed surface. For example, there is some vector function v bar, and then we have a sphere. Then we can always determine a closed integral over the closed surface of this sphere. In this case, the n cap vector pointing outwards is taken as positive by convention. So now let us take an example in order to understand the process to solve this. We'll take a vector, say v bar equal to 2xz x cap. So this is the x component plus x plus 2 y cap plus y into z squared minus 3 z cap. Now suppose we need to find out the surface integral over a cubical surface of this shape having its vertices given by coordinates 2. So this is a cube. In short, this is a cube of sides of length 2. Now in this case, we are asked to determine a surface integral of v bar over 5 of the 6 faces. And the surface to neglect is lower, or the bottom surface is not considered here. So this surface we are not going to consider in this case. As far as directions are concerned, this we can always draw vectors perpendicular to each of the remaining 5 faces, and these are the positive x, y and z directions, whereas the other three are negative x, y and z directions. Of course, this direction is not considered here. So let us consider each of these spaces on case to case basis. Now for this particular surface facing the front, this part, the n cap vector is just x cap, and the surface element in this case, since this surface has a fixed x coordinate having value 2 and an infinitesimally small surface element from this face is going to be dy wide, having a width dy and having a breadth dz. So this dA is just going to be dy dz. So for this first particular surface, dA bar is just dy dz x cap. So v bar dot dA bar is going to be, now since we have only the x component present here, the dot product will also contain the x component. So we have 2xz into dy dz. Now note that x value is 2 here. So we can further simplify this as 4z dy dz. 4z dy dz. Now we can straight away integrate this as integral v bar dot dA bar equal to integral 4z dy dz. Now note that this integral is actually a double integral since we involve dy and dz as well. And we see that y runs from 0 to 2 as this cube is of sides of length 2 and one of its vertices is at the origin, and z also runs from 0 to 2. 4 comes outside the integration. Integral dy is y between lower limit to upper limit. Integral z is z squared by 2 between lower limit to upper limit. So this gives us 4, 2 minus 0 and 2 squared minus 0 squared divided by 2. So this is just equal to 16. So this is just one of the surfaces covered. Now the second surface, which is exactly opposite to this front face, is the back face. The only change in this case is dy dz is the surface element as was in the previous case, since it is the same plane, but the direction of unit vector is now minus x cap. So this implies dA bar is just minus x cap dy dz. But the another change in this case is the value of x, which was in the for the previous surface equal to 2. Now this plane lies at x equal to 0. So here we should have x equal to 0. So this makes v bar dot dA bar is equal to 2xz, the x component of v bar, as we can recall, the x component of v bar, 2xz into minus x cap dy dz. So it is minus 2x, just eliminate that x cap from here. This is a dot product dy dz. But we see that since x equal to 0, putting x equal to 0 here makes everything 0. So the surface integral for this particular surface gives us 0. Now we can keep on doing this for all the remaining surfaces. Just to have a quick go through, we see that, let us, if we consider the surface corresponding to y equal to 2, that is the surface indicated by this portion, y equal to 2. For this particular phase, since y is fixed and dA bar is now, this infinitesimally small surface element is having width and breadth dx dz. Since y is fixed, x and z coordinates change, dx dz, and the direction is y cap. Now for this case, v bar dot dA bar is just, now remember we have to take the y component of v bar. As we can see, x plus 2 is the value of y component. So we have x plus 2 dx dz. And we should note that y is equal to 2 cannot be making any change here, because y does not appear here, as was with the previous case where we had to put value of x in the expression for v bar dot dA bar. So we can integrate this v bar dot dA bar as integral x plus 2 dx dz. Of course, there are two integrations, 1 over z and 1 over x, both of them running from 0 to 2. Now this can be solved. X squared by 2 plus 2x from 0 to 2, and this comes out to be equal to 12. Now we can see that for the fourth surface, we have y is equal to 0 for this particular surface we are talking about, and dA bar is just dx dz into minus y cap, since it is the unit vector is pointing in the other direction. So v bar dot dA bar is just minus x plus z dx dz. So integral v bar dot dA bar, sorry, x plus 2 is here, is going to be, since we can see there is no other change except this negative sign in these two integrals, this is just going to be minus 12. So four surfaces we are done with. Now the only surface left is this top surface. Since we have been told that we should exclude the bottom surface, so let us not do this for the bottom surface. For the top surface, the z coordinate, that is the fifth surface, the z coordinate value is 2. The surface element is dx dy z cap. So v bar dot dA bar in this case would be, now the z component of v bar, y into z square minus 3, y into z square minus 3 dx dy. Since z is equal to 2, this is getting further simplified as 4 minus 3 dx dy, which is y dx dy. Right. So integral v bar dot dA bar is now integral dx integral y dy. So y dy is integrated from 0 to 2 and dx is integrated from 0 to 2. So we have x between lower limit and upper limit, and y squared by 2 integral of y, that is y squared by 2 between lower limit and upper limit. So we are left with 2 minus 0 into 2 squared minus 0 by 2. So this is equal to 4. So the total surface integral over the specified surface is just the sum of these 5 integrals. So integral over surface I, that is plus integral over II, and so on up to integral over the fifth surface. Let us just add up these 5 values. We get, the first was 16, the second was 0, the third was plus 12, the fourth one was minus 12, and the fifth one is 4. So these just get cancelled and we are having the value 20. This is how we solve for the surface integral. We note that both in the case of line and surface integrals, we involved dot products of two vectors v bar dot dl bar and v bar dot da bar. Now as we consider the volume integral part, we see that it is defined directly over some volume v as some scalar function into the corresponding volume element. Note that this volume element is a scalar quantity, whereas these line and surface elements were vectors. So this is just a scalar function in this case. This volume element is a three-dimensional quantity and it is defined in Cartesian coordinates as dx dy into dz. Of course, this need not always be scalar. This can also be a vector in general, and we can integrate accordingly. For understanding how to solve this, let us take an example where a scalar function is defined as x, y, z squared, and the surface over which, the volume over which we have to integrate this is in the form of a prism as shown, x, y, and z axis. Then we have the intercepts as 1, 1, and 3. So this is a prism structure and we have to integrate this scalar function over this volume. Now when we consider this, we have to express at least one of these x, y, and z in terms of the other. Now we see that y runs from 0 to 1, z runs from 0 to 3, and we can claim this if we express x. We have to express x in terms of y. For that, we see that the line belonging to xy plane is a straight line. And the equation of straight line is y is equal to mx plus c. Now we see that when x is equal to 1, y is equal to 0. So if we substitute this, 0 equal to m into 1 plus c. So we get m plus c equal to 0. We see that when y is equal to 1, x is equal to 0. X is equal to 0. So if we substitute this in this equation, 1 equal to m into 0 plus c. So this implies c is equal to 1. Now if we substitute this here, m plus 1 is 0. This means m is equal to minus 1. Now if we use these two quantities here, we get y is equal to minus x plus 1. That is, x is equal to 1 minus y. So we see that along with these two limits, x runs from 0 to 1 minus y. So once we have fixed the limits, now we can integrate them easily. We see that integral t into d tau is integral x y z squared into dx dy dz. Now since there are three derivatives involved, we are going to use a triple integral, each for the coordinates x, y, and z. So let us just write it as xyz squared dx dy dz, where x runs from 0 to 1 minus y, y runs from 0 to 1, and z runs from 0 to 3. Now we see that z is completely independent, so let us just integrate it separately from 0 to 3, z squared dz, 0 to 1. Now we have the y dependence of x. So let us return the y outside and integrate from 0 to 1 minus y, x dx and dy. So this z square dz gives us z cube by 3 between limit 0 to 3. Then 0 to 1 y. Now we have to solve this integral. X squared by 2 between limits 0 to 1 minus y dy, which is 27 by 3, that is 9. Then 0 to 1 y by 2. This 1 by 2 can be taken outside. Upper limit f x square is 1 minus y squared dy. Lower limit is just 0. So this is further 9 by 2 integral 0 to 1 y into. Now this square has to be expanded. So 1 as a minus b bracket squared gives us 1 minus 2y plus y squared dy is equal to 9 by 2 integral 0 to 1 y minus 2y squared plus y cube. We have multiplied y to this bracket. Now this gives us 9 by 2. Now this integral has to be solved. Integration of y is y squared by 2 minus 2 times y cube by 3 plus y raised to 4 by 4 between limit 0 to 1. Now this 0 makes the lower limit entirely 0 and we get 1 squared by 2 minus 2 times 1 cube by 3 plus 1 raised to 4 by 4. So this is just 9 by 2 into 1 by 2 minus 2 by 3 plus 1 by 4. Now this can be solved further. We see that this is 9 by 2 into, this can be solved. 3 minus 4 is 3 minus 4 by 6 plus 1 by 4, that is 9 by 2, 1 by 4 minus 1 by 6. So this is just 9 by 2, 6 minus 4 by 24. So we have 9 by 2 into 2 by 24. Thus we are left with, after the simplification, we are left with 3 by 8. This is how we solve particular problem related to volume integral. This appears to be a bit easier if the surface provided is convenient enough, since we do not have to involve vector quantities if the function is scalar. We do not have to involve dot products when the function is scalar. Thank you.